Hey guys, welcome back. This is Abhishek and welcome to my YouTube channel where I upload AI ML tutorial videos and project videos. So today what are we going to do is anomaly detector by using encoder decoder model, and I will be applying that in credit card dataset. So if you like my work, please subscribe my channel and hit the like button, and this will help my channel to grow up. Okay, so let's start. So in this particular notebook we will cover few things, right? So we will first cover, okay, one more important thing I want to tell you. If you want to find this notebook, you can just go on Kaggle and search for preacher. That's my username, and you can find this notebook. You can copy this all notebook from there and you can work on it, or you can simply create new notebook along with me. So I will be explaining every line of code and I will be explaining every concept behind this notebook, so don't worry of that. And that don't there must not be any doubt in your mind that you can't understand this whole model, right? So you can understand everything even if you are a beginner. I will explain everything. Okay, let's start from the what are we going to discuss in this notebook. So in this notebook you will learn EDA, exploratory data analysis of credit card data, and we will see all the features and their relationship, and then we will see feature engineering, and I will show you that how to create new features and all these things. And then we will see feature selection, and I will be explaining you the histogram way to select the feature. That's really very important whenever we deal with a very high dimension data set. And then we will see some plotting and then we will create our model, that is auto-encoder model. And I will be creating that model on TensorFlow using sequential API. There is three type of APIs in Keras TensorFlow. There is, the first one is sequential, the second one is functional, and the third one is subclass API. So I will be using sequential in this notebook. And then we will see inference phase, that how can we take prediction out of encoder decoder model. But okay, so you might not know that what encoder decoder model is, so let me first explain that. Okay, and then we will move on our coding part. So first we will start some basics to understand that what auto encoder model is, right? So first thing first, let's see first our data set, and then we will talk about that. And one more important thing, if you haven't watched my last videos where I have explained you that how we have implemented autoencoder model on ECG dataset, I have explained that in the last video. You can watch that where I explained you autoencoder model in details, but I will be giving you some brief in this video as well. So okay, so in this cell you can see that I have imported warning because I don't want to get frustrated by just looking at warnings, so that's why I just ignoring every warnings here. And then then I have imported matplotlib.pyplot as plt, that's so obvious, and then cborn, and then config inline backend figure format equal to retina, right? So this is changing the figure format, and this helps the plot to look better in more pixelized way, right, in more clear ways, and that's what we do here. There is two figure format, the one is svg and the second one is retina. svg is a very big file, so that takes a lot of time to load our plot, and that's why we would always select a retina. And then sns.set, what sns.set is, sns.set does whatever we will plot in pyplot in matplotlib, it automatically convert every code, whatever we have written in pyplot automatically converts that plot into cborn. We don't need to write cborn code is exclusively, that will automatically convert it in cborn plotting, right? Now it's time to load our dataset. So I am using credit card dataset, credit card fraud detection dataset. You can look at that. So this is our dataset. It has 8045 upvotes. One is mine of them. And you can create new notebook from here, either you can download it. So I just created new notebook from here, and that's why it's showing up. Okay, So I have loaded this notebook, and you can see few things out of this notebook. So here you can see that we have time variable, then v1 to v28, and then some amount, and then class, right? So what time feature does here? So time feature is the time second, the time in second at which time the transaction has occurred, right? You can see that the data set started with 0 second, and at the 0 second we had two transaction, at 1 second we have two transaction, and so on. And this v1 to v28 v1 to v28 features has created by using PCA, principal component analysis. This is a technique to reduce the number of columns, right? This technique is reduced. Suppose in the data set we have 280 columns, right? So what we do using PCA, we reduce 280 columns into let's say 30 column, 20 column, by preserving 90 to 95, 98% of information, right? And the second reason why PCA is used here, so you can see that v1 to v28 column has been created by using PCA. And the second thing why PCA is used here, PCA have used for data encoding, right? So if you have some very sensitive data which you don't want to share with others in public, so what will you do, you will use PCA technique to encode every data in uh, other form. No one can read that data. So if you have this data v1 to v20, you can't get any information out of it, so you can't misuse the data. So that's what is the second reason to use PCA. And this is the amount of transaction, like $2 149.62 and $2.69 and something like that. And this is class. If it's 0, it means it's normal data, it's normal transaction, and if it's 1, it means fraud transaction. Okay, so now you can see that df.column.values, you can see that we have almost 31 columns, and the class column is our target column, which um, we would like to put as y variable, because this is the column which we would like to predict. Okay, so I think it's clear until now. So let's do some plotting and then pre-processing. So the data set is really highly imbalanced. So how would we say that? You can see this class 0 is almost 284,315, and now in class 1 is just not even 500, it's just 492. Means in the whole dataset only 492 samples are fraud, and the rest are normal transactions. So this is highly imbalanced dataset. So and I have made a video on that how to deal with highly imbalanced dataset using classification, where we have talked about oversampling, undersampling, and smooth and other techniques. You can also watch those videos. But in classification, such kind of problem is not suitable for classification, because such problem gets so many bias thing. Our model at that time when we used classification was biased to the normal. So whatever transaction detail we were trying to give it, all it says that it's normal transaction, right? So this is almost 0.17% fraud transaction. In 100% we have just 0.17% of fraud transaction. You can see, even if we classify every point as normal, we would find out that our accuracy would be more than 99%. So that's why we don't prefer to do this problem using classification. And now we are going to do the same problem using anomaly detection. So keep in mind, just keep your eyes open, and I will be explaining everything. So this data is highly imbalanced, so our classification task will fail. So we will be using encoder decoder technique to make an anomaly detector, right? So we have, what we have done here, we have just df.class 0. So we have just separated out all the normal transaction, and then dot hist method comes from data frame. So this is This is data frame method to plot histogram. So I have plotted the histogram of all the normal transaction, and I have done the same thing for the fraud transaction. And you can see there is one variable, that is time, that is really highly wide. You can see that, and the histogram looks almost similar. And here you can see these histogram of other let's say other v2 other columns looks pretty different, but few looks the same. Okay, so for now we can see the plots, and let's move on. It's so hard to take out information from these plots by just looking and comparing it, so we have another thing to do with. So now we are going to create new features, because the time features contain only second, and that is too wide. So what are we going to do? We are going to convert those seconds into hour and minutes, and then we will try to find out the time when the maximum transaction has happened, and the time when the fraud occurred most of the time. So what I'm going to do, so we know that the tf dot time column gives us the all the second values, all the seconds values. So what I'm going to do, I'm going to change that into pandas time delta object. What time delta object does, time delta creates time delta creates a time delta class, time delta object, and out of that you can convert that into minute and hour and everything, right? So what I have done here, you can see, mm I have changed the time delta in. Then what we have created time minutes and then time hour. So I have converted every seconds into minute and hour, so by using this code. And now what I'm going to do, I'm going to plot. Now let's see the importance of feature we just added. So what I'm going to do now, we are going to plot time hour and the no transaction amount density, right? So figure plt dot figure, I have set a figure size, and then sns dot dist plot and df class 0. So it's normal transaction time hour, and then green. So every normal transaction will looks like in green color, and then for red color this would be fraud transaction. And then given some title here, and then limit, I want this to be from -1 to 25. So you can see this is starting from -1 0 and ends at 25, and then you can see that. So you can find one important thing out of this graph, that most of the transaction happens in between 9 to 23, let's say, means 9 a.m. to 11 p.m. every transaction happened. So that is what we are just trying to say here. But there is no significance, uh, there is no significance information that there is a relation in between fraud transaction and hours. Okay, so I don't think that time hour is really important for this problem, right? So now the same graph for minutes, and you can see this is so parallel. So and you can see that this is so parallel, so we have no much information out of this. And this would be better if we drop this time hour and time minute. Okay, so we will drop it later on when we will be doing a feature selection. I would drop these time minute and time hour there. So now let's try to do some feature selection using distribution graph. So I'm using grid spec because that makes our graph looks so in this form. So you can use these codes for, I have just separated out frauds and normal, and then I'm creating a grid space. So grid space basically creates a grids, and you have to just give index and it will automatically plot at that point. So here I have just set figure and then for n column, and I am enumerating it, and it will plot this sum for like this. And the red one is for fraud and green one is for normal transaction. You can see here our normal transaction and fraud transaction, and then you can see that. But these are not important, but what I want to show you, that is important. Let me show you. Okay, you can see v17, just focus on v17, that the distribution of fraud and normal transaction looks almost similar. It means the distribution uh, it means the distribution is not that much important if I talk about their importance, because if both are looking the same, they can't differentiate if it's model can't use that column to differentiate if it's fraud or normal transaction. So what I would do, I would drop those columns, right? So I'm going to draw a few columns out of v1 to v28. So first I would drop v15. I would also drop v13, and this looks also similar, so I would drop v22 as well. And then I think time minute and time hour must be deleted, right? So v15, v15 I deleted. Why v15 I deleted? Because v15, this graph looks almost similar, you can see that fraud and normal transaction have the same distribution, that's why v15 must be deleted. And and that's why I deleted. So you can see that I have dropped a few columns here, time, minute, time, and all these things. But one more important thing, that if you are not sure about it, right, if you're not sure about the features, you can definitely take all of them, right? So it won't affect your accuracy, but it will not helpful for making a generalized model, that's why. So now what I'm going to do, I'm going to split the TF selected into two part. The first one would be for training and validation, and the second would be for the testing. That will be only for testing our data, right, testing our model. And then what I'm going to do here, I'm going to count some df testing. I would just want to find out how many fraud cases are there in my testing data set. You can see that 98. And then train data, validation data, train label, validation label, I'm just using train test split. And then I'm giving here training data, and then selecting every columns except this class column, and then selecting the class column and stratify and all these things, you can see that. And then at this point I'm using min max scaler for scaling our data. I'm first fitting on the train data. So what train data is it? So here you can see the train data which contains every column except the class columns, and then the same scaling for the validation data as well. And then what we are going to do here, we are going to do the same scaling for the test data as well, because we need scaled data for the testing. If we are training our model on the scaled data, then we must scale our testing data as well. So we are doing this scaling the test data here. So the test data normalize is the variable which has transformed or scaled by using min max scaler. So now we are going to select our autoencoder models. Since I told you that we train our autoencoder model only on the training data set containing the normal transaction, because we are going to train a model who can identify our normal transaction. And if I pass a fraud transaction in our model, it will have a big error. Let me tell you what I am talking about. Let me explain. Suppose this is our autoencoder model. Suppose this is our autoencoder model, and suppose this is a data. Let's say this is a data, and this data is a normal transaction data, right? So what autoencoder model contains? Autoencoder model have first two units. The first one is encoder, right? ENC, and the second one is our decoder, right? This is decoder, right? So whenever I pass our normal transaction to encoder, encoder automatically learn this data and create this whole data into low dimensional data. Let's say if it has 28 columns, it will convert into 5 columns, right? And then decoder will learn how to convert this 5 columns into 28 columns back, right? 28 columns back. So what encoder decoder model does here, encoder encoded the whole data set, whole the data into low dimensional data, and the decoder again converted that low dimensional data into high dimensional data as original, right? So what will happen if I pass only train data, if I train this model only on the train data that contains normal transaction? So what it will does, it our autoencoder model, so the model, let me just back it up. So this model this model uh, we call it as auto-encoder model. So if we train the auto-encoder model on only normal transaction data, then our model will be able to create the normal transaction data, or let's say legitimate transaction data with less error, right? Suppose if I train this autoencoder model with normal transaction data that doesn't contain any fraud transaction data, then this autoencoder model knows that how to create, how to how normal transaction data looks like. So it will convert, it will reconstruct. Suppose this is, let's say this is our normal transaction data, right? If we pass this for testing, right, it will automatically create a normal transaction data graph depending on this one, and then we will compare the error in between the original data and the reconstructed data. If this error would be less, we can say that this error is less because we have trained the whole model on normal transaction. So if the error is less, it means it is normal transaction because the autoencoder model is already trained on normal transaction. But the if error is very high, it means it is fraud transaction because our decoder model have never seen fraud transaction, and that's why it's creating error to reconstruct a fraud transaction, right? Suppose you are an autoencoder model, you have worked on normal transaction, you have never seen a fraud transaction, right? So if you have trained on normal transaction, you will automatically reconstruct the normal transaction because you have seen that. And if you have never worked on fraud transaction, and I will give you a fraud transaction to reconstruct, and it would be more probable that you will make mistakes, you will make error because you have never seen a fraud transaction data. So using this concept, we use anomaly detector using autoencoder model. So what I'm doing here, I'm just splitting out here normal train data, normal test data, and normal validation data. Why we are going to do that? Because we will train our autoencoder model only on the normal train data, which doesn't contain any fraud transaction data. So for that reason, I am just changing every train label, validation label, test label that contains 0 and 1 into boolean that would be true and false, and then selecting out all the normal transaction data, and then selecting all the fraud transaction data out of train data normalized. Okay, you can see that we have this much this many number of fraud transaction data and the normal transaction data. Now we can plot it. So I'm using matplotlib, as you can see here. So this is how our normal transaction data looks like, and this is how our fraud transaction data looks like. So we would train our model to create normal transaction data, to reconstruct normal transaction data. So we will pass only normal transaction data. So let's build our autoencoder model. So we have to import uh, callbacks, early stopping, and activation loss optimizer matrices. And then so we have created a sequential APIs here, and then adding layers on in that. And then this is our encoder part where we have given dropout, and then this is our low dimensional unit, which is 5. So earlier the data has 25 columns, and the low dimension would be 5, and low number of dimension would be 5, and then this decoder model will automatically convert this 5 units to again to 25 columns. So first it will encode and then it will decode, and then I'm compiling it, and here this is encoder decoder, I'm compiling it. And now as you can see here, this is I'm defining an early stopping, and then history equal to auto-encoder.fit. Here I'm giving x equal to normal train data because we don't need to pass any fraud transaction data inside it. So we have filtered out all the normal transaction data and passing it in x. And y equal to y would be the same normal transaction data because we want to test we want to compare the reconstructed data with the original data, right? And that's why we are giving the same normal transaction data. And then epochs equal to 100 verbose, and validation data is here. This is validation data. We are passing the normal transaction data here as well because we are not we have no concern. We want our model to create much error when we pass fraud transaction data. That's why we don't need to pass here the whole data in validation dataset. So even if in validation dataset we will only pass the normal transaction data because we want our model to um, become so accurate while creating the normal transaction data, not fraud transaction data. So that's why. So you can see it has ran almost 13 epochs, and we have got these things out of here. And you can see we have validation loss as 3.44.64. So as low as you will have this loss, you will your model will create less error while reconstructing the normal transaction data. So uh, so you can also use here LSTM model. That would be, I will leave this task on you, so you can create the whole model with based on LSTM, and you can find out that LSTM model, encoder decoder model based on LSTM will be more accurate. Okay, so this is just a baseline model. So now you can see that I'm plotting something. So this is the function I have created for plotting, and I'm passing the normal transaction data, and that comes from test data which we have split it out at the very beginning. And this fourth defines that we are using the fourth sample. Suppose you have 98 samples, so you can take this end up to 98. So here you can see that our model creating less error while creating the train data, and it's creating more error while creating the fraudulent transaction data. For normal you can see less error, but for fraudulent transaction you can see the more error because our model never seen any fraud data. Now it's inference stage. So what I'm going to do, I'm going to calculate the losses mean absolute error for construction of normal train data. You can see that the mean of normal loss comes out is 0.116, and this is our plot about that. But if we do the same thing for fraud data, here you can see that the error is 0.11 for normal transaction data, and the fraud transaction data you can see it comes out 0.5. So the fraud transaction data error is big much higher, 5 times higher than the our normal trend data, right? So using this fact we can set a threshold, and we can say that if the loss is greater than this value, we will say that this is a fraud transaction data. So for that reason, through setup threshold, let's say that our whole data have 2% of fraud transactions. So on the base of that you can calculate, let's say that our data have 1% of fraud, so you can uh, calculate the percentile and you will get a cutoff for threshold value. And this is train loss, and this train loss contains every fraud transaction and normal transaction, and we will get a array of all the losses. all the mean absolute error values, and then I'm selecting the 1 percentile highest, because we are assuming that only 1% we have 1% of fraud data, and that's why we are selecting out 99 percentile. So I have got this threshold value, and now I'm just, what we have done, you can also do the same thing. You can also do the same thing by using np.mean and then adding with some standard values. You can do that as well. I'm giving 5, but as you know that if mean plus 2 into standard deviation, if we move to standard deviation, we already covered 97% of the whole data, and it comes from statistic. Now it's time to prediction, so I'm creating a list here. So for what I have done here, we have tested data normalized. We have normalized our tested data. Now I'm going to predict on based on that. So here auto-encoder.predict, it will give me reconstructed values, and then I'm going to kind of calculate the mean absolute error of reconstructed with the original data, and then we will get error, and then I'm using an loop, and if error is greater than our cutoff value or threshold value, I will say that this is gonna be our fraud, otherwise it would be a normal transaction. So you can see that. And now I'm just doing that. It has predicted that 622 fraud transactions just to capture 98 fraud transactions. So this is our, let's say this is our classification report. You can see to identify normal transaction data, it's almost the perfect, and to identify the fraud transaction data, this its recall is almost 80%, and precision is not that much good, because it has so many let's say it has so many false positive, because if it's saying almost 545 false positive, because to detect 98 fraud transaction, it has giving up almost 622 fraud, and that's why it has false positive, and that's why precision is less. But whenever we talk about anomaly detection, we just try to filter out all outliers, or let's say all fraud transactions, and on the basis of just we don't want to compromise with precision, and that's why. So we have 79% recall, and this recall is good. Almost 77 fraud transaction has been detected out of 98. Now I'm just creating a big not that big, but I'm creating data frame for normal transaction data, and then abnormal, or let's say fraud transaction data, and I'm plotting it, right? So you can see that this dashed line is our threshold, and these blue lines under this dashed line is our normal transaction data, and this orange line, whatever line is above this threshold, is our fraud transaction data. And you can see there some orange line is coming under this dashed line, and that means that those are fraud transaction data, but they lies under threshold, and they have treated as normal transaction data. So you can fix this problem by using a better model in autoencoder. You can use LSTM, and I leave it on up to you, and I will also create a video on using LSTM model as encoder decoder. When I have created that, I will upload that as well. So stay tuned, I will also upload that video as well. And again the same again different graph. Now you can see this dash line. So whatever data comes in afterward this dash line are fraud transaction data, and there is some few lines which is behind this dash line, they are also a fraud transaction data. So you can see there is some mistake here. um, this is some limitation of our anomaly detector model. You can fix up that by using LSTM or GRO based on that. So final takeout, we can improve this model by using LSTM encoder decoder model. More training data makes better result, and this is anomaly detection, and it can take it as classification problem, but that will work. So I hope that you like this video, and if you have any queries, any problem, any questions, you can simply comment on this notebook, and you can see there are lots of comment already here. You can also post your comment. You can see that I have almost replied to every comments here, so I will also reply you there. So thanks for watching this video, and if you really like this video, please do share and subscribe, and it will help my channel to grow up. And one more important thing I just want to tell you, I just want to share the notebook link in description box. You can download from there, or simply you can search preset, and then uh, you can navigate to my notebook. And thanks for watching this video, and have a nice day.